Hello everyone and welcome back once again. So right now we are talking about strain edging in aluminum alloys, and with regard to that we have started discussing about the Cottrell-Bilby theory of strain edging. So in this lecture today we are going to continue on that.
Yeah, so I think we started from here, right? We are talking about a solute atom which is lying somewhere at a particular distance from an edge dislocation, right? So we started from this diagram, if you remember. So here is the slip plane on which the dislocations move. And from this, simple diagram, you can get this equation which relates the interaction energy to these two parameters, r, which is the distance, and theta, which is the angle between r and the slip plane. Okay. So from here, what we basically derived was this equipotential lines, which are basically the value of this interaction energy u. Okay, and for a fixed value of u, you will get these circles passing through the dislocation line. Okay. And we have also seen that the largest value of u corresponds to the smallest circle. Okay. So there is a variation in the interaction energy as you move from the dislocation, right? So due to that energy gradient, we have a force which is experienced by the solute atoms, right? So this is what we discussed in the previous class. And due to this force, the atoms may gain a drift velocity, which is given by the Einstein equation. Okay. So up to this, we have discussed in the previous class. So here, you have this diffusion coefficient because we are talking about the flow of atoms over here. So the diffusion will come into picture. And as you know, diffusion is all about movement of atoms through the lattice. And the diffusion coefficient D basically describes that atomic mobility in terms of movement of the atoms from one lattice site to another, or from one interstitial site to the adjacent interstitial site if it is an interstitial atom. Okay. So now you will have to see how this movement occurs and what is the path of this movement in order for us to get to the dependence of this atomic flow on the time and temperature. Okay, so that is what we wanted to derive from this equation. If you remember, we want to derive and we want to know how the atoms flow. Okay, and what is the dependence of that particular flow on the time and temperature, right? Because here we are talking about a phenomena called strain edging, and it is about the interaction of solute atoms with the dislocations. So how the solute atoms move towards the dislocation, that is what we are trying to understand over here. Okay. Right, so this is what I said. The diffusion coefficient D describes the atomic mobility, that is the atomic jumps between adjacent sites. Now we need to understand as to what is going to happen to this atomic jump when you're talking about an energy gradient. Okay, so if there are no energy gradient, then statistically these jumps will be random. So let us first see, if there is no energy gradient, how these atomic jumps will happen. And as I said, in the absence of an energy gradient, statistically these jumps will be random, and therefore the concentration will remain homogeneous. What it essentially means is atomic jump in a particular direction is balanced by equal number of jumps in the opposite direction, right? So that is why the concentration remains homogeneous. Okay. But now we have seen that, here we have an energy gradient, right? The energy varies as you vary the value of u. So under the influence of this energy gradient, how this atomic jumps going to be? That is what we need to understand, right? So when you have an energy gradient, you cannot expect these jumps to occur randomly anymore. Because jumps tend to become more frequent in a direction of decreasing interaction energy. And this will essentially result in atomic flow along the energy gradient, right? And the other thing that you can note over here is the fact that the maximum energy gradient occurs in a direction which is normal to the equipotential line. So let us go back to those lines. Here are they. Right, so the maximum gradient occurs in a direction which is normal to these lines, right? So that means I'm talking about a direction which is like this, which is normal to this line. That means it is along this circle. Right, so this path basically is the path for the atomic flow, because as I said, it occurs in a direction which is having the maximum energy gradient, right? So atoms will tend to flow along this path, which is depicted by this dotted circle over here. And therefore, this is the flow path of the atoms, and these lines are therefore known as flow lines. Right, so this is that R, okay, because here you have the dislocation along this x-axis, right, and this is the theta. So the same diagram that we had over here can be now brought over here, because now we know in which direction the solute atoms are flowing, right? So that flow direction is along this blue circle that you see over here, okay? And the mean energy gradient across a circle like this can be given by so this is the circle which represents the flow lines, okay? So along that, the mean energy gradient, that is du by dr, will be this, that you can again obtain from that particular diagram. And we have also seen that this energy gradient is responsible for the force that the atoms experience, right? So therefore, this can be also written as equal to F. So now if you come back to this Einstein equation, and replace F over here, then you would get this expression for V. Right? So let's call that equation 2. Now, if T is the time for an atom to move completely around a circle of radius R1, okay, then V is simply R by T, right? And from here, and using equation 2, we can obtain T as this. Let us call this equation 3, right? So now we have an expression for the time taken for the solid atoms to move along a particular flow line, right? So now you have several of these flow lines, like how you have several of the equipotential lines, right? So if this time corresponds to a flow line of radius r1, then we can say that by this time all solute atoms lying within the circle of radius r1 should have moved up to the region under the dislocation, right? So this will be the time taken by the solid atoms to move around this radius r1 completely and go to a region below the dislocation. Okay, but the other circles that you have having higher radius will still be active, and they will continue to supply the solute atoms to the dislocation line, right? Because as I said, there are multiple of these flow lines. So once once the flow is completed along a particular radius, it will start to the next ones and so on, right? So when it is completed in a particular circle having a particular radius, it will still be active in the other circles having larger radii. Okay. So now if you consider a small time increment dt and see the accumulation or movement of solid atoms over this time increment, in this time increment, each of the flow lines will add a number of solute atoms to the dislocation, and therefore you can expect the length of the dislocation line to increase. So from a length increment perspective, this accumulation of the solute atoms underneath the dislocation will be given by this expression. Right? So this is the solute accumulation in a time increment, in a small time increment dt, right? So if you want to know the total accumulation of solute in a particular time interval, then you can simply integrate this over the range from r equals to And this expression for R comes from this particular equation, right? From here, from equation 3. Okay. So if you integrate this from R equals to this to R equals to infinity, then you will get the total accumulation of the solid atom in the time increment. That means in this time period t plus delta t. So in this small time increment, the total solid accumulation can be obtained by integrating this from R equal to this to infinity, and that will give you this. Okay, so this is the total solid accumulation, which basically represents the area that supplied solute atoms between time t and t plus delta t. Okay, between t and t plus dt. Okay, right. So this factor 2 comes because there are flow lines on both sides of the dislocation, right? As I showed over here, you have the flow lines on either side, on right hand side, as well as on the left hand side also, simply because equipotential lines are on both the sides, and since the flow lines are normal to the equipotential lines, you should have the flow lines on either side of the dislocation, right? And that is why this factor 2 comes over here. Okay, right. So from here you see how the solid atoms are moving and what is their flow path, right? And we are also getting to this time dependence because now we have an expression where this time t is there, right? So we are trying to understand what is the kinetics or the time dependence of this process as to what power of time this flow varies with. Okay, so this is one thing that you can derive, this expression for the time with regard to the flow of the solute atoms for them to build up around the dislocations. And the other thing that can be derived from this theory is the fraction of the solute segregated to the dislocations, okay, in a particular time. So if you look at the number of segregated solute atoms on a unit length of dislocation, let us call that NT, which is number of segregated solute atoms on a unit length of dislocation. And this is given by this particular expression. Where alpha is a constant with a value approximately around 3, and N0 is the initial number of solute atoms per unit volume. Right, and from here you can also get the fraction of solute segregated to the dislocation. If you simply divide this NT multiplied by the dislocation density rho by N0, you will get this fraction of solute segregated to the dislocation. So as I said, that is nothing but NT multiplied by the dislocation density rho divided by N0. And if you substitute NT over here, this will give you this particular expression for the fraction. Right, so from here you can see that the rate of arrival of the solid atoms varies as t to the power 2/3. Okay, so this shows you the time dependence of this solid segregation along the dislocations, right? And for longer aging time, there is a generic expression which goes as follows. Right, so this is the expression of the fraction of solute segregated along the dislocations for longer aging time. Right, so from here you can see the dependence of this solute segregation or this build-up of atmosphere of solute around the dislocations on the time as well as temperature also. And this is what we wanted to know. If you remember, we started with this objective of knowing how this solid atmosphere build up depends on the time and the temperature.
All right, so with that, we come to the end of this lecture. Thank you for your attention.